part of the 1.2 function transformations. So we're going to be looking at reviewing how to stretch and shrink and shift up and down, left and right, some reflections, the different types of things that you learned in both your Algebra 2 classes and in your pre-calc classes. This is one of the most important skills in calculus for success, because when you're looking at a function, you kind of have to have that knowledge of what a function looks like. You have to be able to see the graph, to visualize the graph in your mind so that you can answer questions quickly and accurately. Now, so the parent functions, you've done the Desmos activity at this point, and so that gives you a good review of which parent functions right now that I want you to be familiar with. The ones that so far aren't in the list are going to be some of the trig functions and logs and exponents. We're going to review those separately in one of the next sections in chapter 1, but you do need to kind of know their basic parent functions and their basic shapes that we're going to be looking at. The second thing that you need to know is how the coefficients in the equation, the numbers that are in front of the function, in front of the x, that's added to the x on the inside, added out on the end, all of those coefficients transform the shape of the graph. And those are the things that you need to be able to work with. So what we're going to review today's lesson is how to identify the parent function, which one, the shape of the function we're transforming, how to look inside the function and start with horizontal transformations. And just to recall that graphical transformations are usually opposite of what you see in the equation. If it's a +2, it goes left 2 and those kinds of things. How to look outside the function for the vertical transformations, and those are matching what you see in the equation instead of opposite. The reason for this has a lot to do with inputs happen before the function, outputs, transformations happen after the function. So that's a little bit why the before function gets reversed, but after the function is in the normal order that we look at it. Now, we also want to be able to numerically describe what happens to the original anchor points using a transformation rule, or it might have been called an anchor point rule in your class last year. So notice that we are doing this idea of this rule of 4 when we're looking at it, because I'm giving you an equation, algebra. You are then visualizing what the graph is going to look like graphically. You're going to verbally describe what's happening and be able to write a transformation rule, and then you're going to be able to tell me what original points got switched to what new points and so on. So they're all things that are going to be important as we work through some of these examples. Here is kind of the basic. We're going to do these one by one first, and then we'll kind of put them together. So in this one, what we're looking at is we've got this plus d on the end, and d is a coefficient. It's just a number that's being added outside the function. And so recall that vertical transformations are the same as what appear in the equation because it happens after the function. You graph the function f of x and you shift it up d. You just add d. If d is positive, it goes up, and if d is negative, it goes down. So that is our vertical translation. Very simple. Here is the black is an original function. It's just a cubic polynomial. And to shift it up, we add 3 outside of the function, and then it moves it up 3 here. Notice that all the key points, this intercept here at 0, 0 becomes 0, 3. The max, which looks like it's about 1, 3, becomes 1, 6. So you see that the anchor points, the y values, are being changed by adding 3 to those. And then the blue graph, of course, is shifting down 2. So the original had a 0, 0 becomes 0, negative 2. The original had a min at 1, negative 3, and it becomes 1, negative 5. So you can kind of see how the points are changing as we work through that. We also have horizontal translations, and again, this is where you have to be careful that it's going to be the opposite, because it's going to happen before. This x minus b is, in order to put an input into the function, it has to be the same input you used to put into it. So you're going to have to undo the minus b in order to figure out what happens, and that's why it ends up being reversed or backed up to say what would you put into this to get the original input that you would have had to the function. And so it always ends up being opposite of what is happening. So this minus b, if b is positive, Okay, so it would be minus like 2. If B is, I think I typed, is this typed in wrong? Oh, I think it's because when they have the minus right here, if it's minus 2, then B would be positive and it goes right. If it's minus negative 2, then that really is plus 2, and that's where the opposite is coming in. Because you have to factor out this minus that's right there, if that makes any sense. So it's identifying that it has to be x minus, then the horizontal translation will tell you which way to go. And that's why it looks opposite. So like right here where it says f of x plus 3, that's really x minus negative 3, so it goes left 3. So this is the red graph, and you'll see that here's 0, 0, goes over here to 0, or goes to negative 3, 0. And you see that the x is what is being changed, and you are subtracting 3 from it, and it's the opposite of what's inside of the equation. Over here we have f of x minus 2, so b is 2, which is telling you that it's going to the right 2. And you'll see that from the original, the 0, 0 becomes 2, 0, and you are adding 2 to that. So, and again, notice I'm kind of talking about showing you words, verbal, what's happening in the equation, algebraic. Here's a picture, the graph, and then I'm also discussing points, and that's the numeric representation. So we have this rule of 4 that we're looking at. All right, let's look at vertical scales. So again, we're back on the outside of the function. So again, it's going to be exactly the way that it's written. It's not going to be opposite. It's going to be the same. It happens after the function. So we take our function, and afterward we multiply it by c. And right now we're going to consider c to be a positive number. We'll talk about what happens if it's a negative number in another slide. And it basically is going to be a scalar. We're going to either stretch it or shrink it vertically, which means that it's either going to get shorter if it's a vertical shrink, and that's when c is a fraction. So you're doing like half of your output. And a vertical stretch or taller if c is greater than 1. So, I know that visually you might be looking at this and be saying, well, it got skinnier, but that's not what we're looking at. If the black is my original, and I'm going to look at this point right here where I have the yellow little highlight, if I am shrinking it by 3, okay, which is the 1/3 f of x. It's a third of what it used to be. The height is a third. It's coming down, the matching point is right here below it. So it's taking the y value and multiplying it by 1/3 and shrinking it down. So it's becoming shorter. That's what we're doing with a vertical shrink. And then a vertical stretch will take this point right here and stretch it and make it taller and move it up. And so it's a stretch or a shrink. Now, what gets a little confusing, especially when you use parabolas, is that there is a coordinating horizontal scale that does the same thing. But we're not talking about that right now. We're saying that if there is a number multiplied on the front, it either vertically makes it taller or shorter, depending on what it is. All right, then we have vertical reflections. So let's talk about what happens when c is negative. When c is negative, then we have a vertical flip, and a vertical flip is over the x-axis. So you can see here that depending on the actual, number that c is, there's two things going on when you're negative. You have a flip and a stretch, or a flip and a shrink. So like you'll take a notice, the black is still my original, and if I have negative 1/3, I am flipping it and I am making it shorter. So that's why it's closer. See how from here to here, the distance from the bottom of the graph of f of x to the x-axis has been flipped up and then shrunk, made shorter than what it was. So the distance from the origin up to that peak is exactly 1/3 of what the distance was from here to there, and it has the flip and the shrink. So you do both things when you have it. And then like the other one is the pink one. The pink one has a -2 in front. So it flips it and stretches it by 2. So again, if I look at the distance between the origin and the minimum here, I flipped it, and then the distance from the origin to this max now should be twice the distance that it is because I made it 2 times taller and flipped it when I looked at it. Now, horizontal scales, that's also something that we want to look at. Now, in that one, remember that on the inside is always opposite. So, because of the undoing it, the stuff that happens before. So, when we talk about how you're scaling it by what factor, our factor is actually going to be the reciprocal of A, because the opposite of multiplying is dividing or reciprocal. So if this was a 2 here, like this f of 2x, now remember this is happening horizontally. So we're either going to get wider or we're going to get narrower. So we're either going to push it in or we're going to pull it out from the y-axis. So here's my original, y equals f of x. The pink is f of 2x. And notice that it's a 2 on the inside, but what we're actually doing is, because the 2 is greater than 1, the opposite would mean that we are shrinking it by a scaling factor of 1/2. It's 1/2 the width. If I compare the width from here to here to the width from here to here, the width of the pink one is going to be half the width of what the original was. And then if you have a fraction like here, notice that it got wider. So it does the opposite of what the number is in there, because we're doing the reciprocal of it to determine our scaling factor. And then we talk about our horizontal reflections as well, that if the A inside right here is a negative number, what is going to happen when we take a look at it? So if A is a negative number, you're going to flip horizontally, and that's across the y-axis. So you'll notice that all of these, the original is black, and notice that I flipped it across the y-axis over to this side. Now I also, in this one, because it's f of negative 2x, I flipped it and I shrunk it to be half the width that it used to be. So if I were to compare the distance from the y-axis out to a corresponding point here, and the distance from the y-axis to the point on the other side, it would be half the distance. That's the scalar that we're looking at. And then again, here's the f of negative 1/3 x, that the negative flipped it, and then the 1/3 made it 3 times wider when we were talking about it. All right, so in general, and I may have changed these letters. I mean, it's one of those things, if I'm only talking about inputs, they might have had an A there. Don't let that name of it get or confuse you. When you are talking about this, these names don't matter. I could use P, Q, R, and S. It's just that if I have all 4 of them in there, I have a tendency to write it with left to right, A, B, C, D. Notice also that this is what's called the transformation form. Do you see how the coefficient on the x has been factored out? And that's because this is going to give you kind of a way of looking at it that reveals the transformation without you having to do the x old, x new analysis that we did probably in one of your prior classes. I'll review that as well, but I wanted to show you the transformation form, and that's the way that I taught it when I did this, is that you factor it out, because then it makes it easy to read what transformations have happened. So here's our nice little function that we're looking at, and our first job is to come up with what the parent graph is. What's the shape of the graph before we transform it? Now, in looking at this, you kind of have to identify that there's an inside to some function, and then there's stuff outside of that function. So when looking at this, because it's got that square there, I'm going to identify that the parent is the square function, or the shape of the graph before I start is going to be a parabola. From that point, I always do the horizontal stuff first to kind of talk about what's going to happen. I initially look at this coefficient, the scalar, and I say to myself, is that negative? And the answer is no, it's positive. So immediately I know that there's going to be no flip. Also remember that the inside function is opposite when you're doing horizontal transformations, so that's also something to kind of pay attention to. So B is greater than 0 right here, so no flips, so there's nothing going on there. Then I identify that B is greater than 1, that it's 3, and I remember that I do opposite. And when I do opposite, that would mean that I am multiplying the width of the original by 1/3, so it's going to get narrower. So I know when I write down like all the things that I could say verbally about what's happening here. The absolute value of B is 3, because again, we've already taken into account the flip. It's a horizontal shrink by 3. That's one way that we say it. 3 times narrower is kind of what you look at. Your scale is a scale by 1/3. You take your original x coordinates and you are multiplying by 1/3. Your scale factor is 1/3. It's 3 times narrower. The new width is 1/3 the old width. And so that's kind of where you're talking about, shrink by 3 is the same as saying multiply by 1/3. Shrink gets smaller, 3 times smaller, or multiply by 1/3, which has the same effect. So that's kind of the words that go with that. And then our horizontal shift, when we have factored out the 3 and we have it in this form, then the number that is there is exactly the horizontal shift, remembering that you have to do opposite. So it's -1. So in our head, we know C is 1, which means that we went to the right 1. Okay? Because it's got to be, if it was a +1 there, then C would be -1 and we went left 1. So it always does the opposite for that. So in your head, graphically, you're just visualizing that I started with a parabola, I made it 3 times narrower, so it's skinnier, coming across this way, and then I also shifted it to the right 1. And that there is an order of operations for this. When in this form, you pretty much always do the reflection, the scale, and then the shift first. Okay? That's kind of how that is when you take a look at it. Then we identify what's on the outside of the function. And the stuff that's on the outside, the -2 and the +4, that's the output transformations. And those are the same as written when you go through this. And they're usually the easiest ones because you don't have to remember to do opposite. So I have the -2 is going to be my A value in this, what I'm calling it. So this A is negative, so I know that there's a vertical flip, an up to down flip over the x-axis. So now you're going to visualize your parabola flipping down. So we took the parabola, we made it narrower, we shifted it to the right 1, and now we have flipped it down. So we're just kind of keeping that in our head for our visual. Then we look in the fact that the absolute value of A is 2. So there's a vertical stretch by 2 because outside does exactly what it is. It's 2 times taller than what it used to be. Our scale is going to be 2 times, and the new height is twice the old height. So if I were to compare one anchor point to the new anchor point, it would be twice the height that it used to be from the x-axis. And then our last is the +4, our vertical shift. So when we take a look at that, our vertical shift is going to be going up 4. And so we've taken our nice flipped graph that we made taller, and then we're going to shift it up. So we can kind of visualize where the important features of the graph are. All right, let's take a look at it graphically and kind of run through those steps that we just kind of came up with. We had our original parabola. We made it 3 times narrower, or we multiplied every x value of the anchor points by 1/3 to get the new anchor points. Then I took it and shifted it to the right 1. So I'm just kind of deleting the original and leaving only the previous step. So now I'm in right 1. Then I did a vertical flip and made it twice as tall. That's going to be a little bit harder to see when I do this, but if you compare, like right here at 1/2, it goes to about 2.5, and now at 1/2 it goes down here to -5. So there was also a flip, and I stretched it and made it taller from the x-axis. And then the last thing we're going to do is we're going to shift it up 4. And so that's kind of the visual of what your head is thinking as you're going through this, to know that it ends up with a vertex in quadrant 1, that the vertex itself is going to be at 1,4. And that's one of the things that we talk about. So we've kind of done this verbally from looking at the equation, which is the algebra. We've looked at the graph and we've visualized what's going to happen. Now let's look at our points. So what I have here is only the original parent graph right here and the new one. And you can see here that the original anchor points, I'm using the very standard -2, -1, 0, 1, and 2. as points that I'm going to look at. And then I have the new points that correspond to them here in red. And let's take a look at what we did. So if I take the verbal description of what we did, we made it 3 times skinnier, okay, narrower. So that was multiplying by a scale factor of 1/3. So that's the 1/3 x old. And then I shifted to the right 1. So that's my +1. That's how I'm changing the old anchor point to get the new x value of the anchor point. So this is my transformation rule for the x's. And then over here, the y's, I flipped it. That's the negative. I made it twice as tall, scalar by 2. And then I shifted it up 4, so I add 4 here. So notice the difference between them. Remember, this is the opposite, whereas this was exactly the same. Now, if I'm looking at this right here, if I were to actually take that and set it equal to, like, call this x new, set what's inside here in yellow equal to x old, and solve for x new, that would give me this rule that I have right here. So that was kind of the new old analysis that you might have done in your class as well. And then here I just plug and chug. Notice I plugged in the -2 from the original. I plugged in -1, 0, 1, and 2. And that's how I'm getting this 1/3, and I think this is 2/3, 1, 1 1/3, and 1 2/3. And so that's how I'm getting the new anchor points. And then over here, notice I'm plugging in the old y values that I had on the original anchor points. 4, 1, 0, 1, and 4, and that's where I'm getting the -4, 2, 4, 2, and -4 again. So that's kind of the numeric analysis that you would be thinking of. All right, so let's do a practice problem. One more. Now this one, I made it a little harder because notice that I do not have this in transformation form. Do you see how I don't have that coefficient, that 1/2, factored out? So that's the first thing that you need to do in order to really utilize this equation. So the first thing is to rewrite it in transformation form. So I'm going to pause here, or you pause the video. I'm actually going to throw up these as questions in the Ed puzzle, and I'm going to ask you each of these, and then I'll show you the answer. So your job is to first rewrite this in transformation form. So pick up your pencil and do that. I'm going to pause for a second. I'm going to ask you the question in Ed puzzle. You're going to input your answer, and then I will show you the answer. So I'm just going to pause for a second. All right, so here is my transformation form. So notice that when I pull the 1/2 out, that remember that what you want to have to get this to be correct is that this 1/2 times the number that's right here, the -2, has to end up being this -1 up here. The other way of looking at it is saying that when you pull out the 1/2, you divide what you have here by 1/2. And 1 divided by 1/2 is 2. And that's how I get this into the transformation form that's there. All right, next question is going to pop up is, can you tell me the numeric transformation rule? That's the anchor point rule. So you're going to write x new equals what's your scaling factor times x old, and your translation, what you're going to add, and then your y new equals. So write your x new equals first, and then write your y new equals, just looking at this. Now I'm not graphing it, I'm not doing anything, I'm doing it straight from the equation to write it down. So you answer that in Ed puzzle, and then I'll show you my answer. All right, so in doing the kind of transformations, the fact that this is a 1/2 right here, I remember that you do opposite because it's inside. So that would be a stretch, horizontal stretch by 2. It would be twice as wide. So I multiplied my x old by 2. Then I have a -2 here. So the 2 is what is telling me what's happening in the shift. So it's going to go right 2. And again, look that it is opposite of what is in there. So 2x old plus 2. Again, you could simply take, instead of doing this transformation form, I could take this 1/2 x minus 1. I could call this x, x new. I can set it equal to x old, and solve, and I would get this same thing. You can verify that for yourself. I don't really care how you do this. I just need you to be able to tell me what transformations have happened. And then, of course, the output transformations, the stuff that happens outside the function. And I didn't ask for the parent graph, but hopefully you realize the parent graph is square root of x, because that's the function that's shown. So the things that happen on the outside, 1/3 and -3, are the output transformations. And they do exactly what it says because they're outside. So I have a vertical shrink by 1/3 and a shift down of 3. Now, let's figure out the endpoint then. Once you have this transformation rule, then the original endpoint of a square root graph, if you picture it, it starts at 0, 0 and kind of comes up over into quadrant 1, a little concave down graph. So when we look at that, the original endpoint, I want you to state that, and then state the new endpoint, and you can use these rules to help you figure it out after transforming. So I'm going to put that up in Edpuzzle, give me your answers, and then I'll talk about mine. All right, so the original endpoint is 0, 0 for the square root graph. Remember, picture the little half parabola that a square root graph is on its side. And then you take a look and see the new endpoint, and I basically just plugged 0 in for x old, 0 in for y old, and I just simplified that to get the new endpoint is 2, -3. All right, now we're ready to go to kind of visualizing. Notice I'm not actually graphing this. I'm just going to visualize to myself what this graph looked like originally, and then what this graph looks like now after the transformations. And really, once you've got the shape down, oops, of course that didn't, let me go back, and back. That once you get the shape down, then you're just visualizing. So I know, and it's hard because I don't know whether I'm going to be mirrored or not, but I have an endpoint at 0, 0, and it goes out into quadrant 1. So then I ask myself, kind of thinking about domain and range, originally the domain is 0 to infinity for both x and y, okay? Because it starts at 0, 0 and goes to the right, and it starts at 0, 0 and it goes up. And so those are the two things that we think about for domain. Now, what happened in these transformations? Really, what I want to know is where did the endpoint go, which we've got 2, -3. And then the question is from that point, do we still go to the right and up when we do the little shape, or was there a flip in it? So I take a look at my transformations and I say, well, there was no horizontal flip and there was no vertical flip. So yeah, from that endpoint, it still should go from the endpoint to the right, and it should go from the endpoint and up and heading out over in that direction. So the domain and range, think about that and go ahead and write your domain and range in interval notation for me. All right, and then what you would see is from the x value to the right is going to be my domain, and then from the y value and up is going to be my range for that. So I don't have to actually graph it, although I should have a nice visual of where the 2, -3 ends up down in quadrant 4, and I'm going up and to the right from that because there were no flips. So that's kind of how we're visualizing as we are doing a lot of our transformations, to just kind of be able to answer questions in our head about what's happening. I could also ask you things like, this function is increasing from 2 to infinity. This function is concave down from 2 to infinity. This has an absolute min value of -3 that's happening at x equal to 2. So there are things like that, those characteristics that you did back in pre-calculus, that are going to be important as you kind of work through these types of problems. And I think that's the end of this little lecture. Hopefully that will give you a good review of transformations from your pre-calc and Algebra 2 classes, and be able to work through some of the questions that you have. The transformation circuit, I believe, is going to be our next activity where you just practice all of these. Let me know if you have any questions. I'll be available through office hours on Friday.